Welcome to Altair Engineering Training and Support. I am Apurva Bhatt. Today in this training series I am going to discuss about the solid thinking inspire. We'll see with this training series schedule. In the previous session, that is session 1, 2, 3, 4 and 5, I have discussed about how to apply for the license, how to download the license and install the software, how to activate the license of STInspire 9.5, basic and modeling operations in SolidThinking Inspire 9.5. In today's session, I am going to discuss about the optimization operations available in STInspire and how to use them. Then in the later session, I will start showing with the tutorials in getting started. Tutorials for moving and snapping, tutorials for sketching and optimizing a bridge, tutorials where I'll show you exploring multiple load cases, preparing CAD geometry, defeaturing a model, minimizing mass, saving and exporting files. So in today's session I'm going to discuss about design space, pattern repetition, loads and displacement, shape controls, running optimization. So these are the things which I'm going to discuss. So let's start about the basic theory of optimization, where it states that optimization is the process of generating a shape in response to load cases and is the core of SolidThinking Inspire. The optimization process carves material away from the design space, creating the lightest structure capable of withstanding the force you apply to your model. Note that optimization only works on parts that are defined by solid geometry. Parts which are mesh, such as imported STL files or FEM files, are ignored. In order to perform an optimization, you must first define a design space and one or more load cases containing both loads and supports. You can also apply various shape controls such as symmetric planes, cyclic repetitions, and draw direction as well. You then run an optimization and await the results, which can take a few minutes to few hours depending on the complexity of the model. Once the results are complete, you can interactively explore variations of the resulting shapes. Not all parts in the model need to be design space to run an optimization. In many cases, you will need to apply loads and displacement to the parts surrounding the design space in order to properly define your model. However, only the design space itself will be optimized. Note that any part that are in contact with each other are considered to be welded together with no slippage. This section explains how to define load cases, apply shape controls and run optimization. So let's start with the design space. Design space is the initial part from which material is removed until a final shape is reached during the optimization. You can create a design space by using the modeling tool in Inspire or by importing parts from other solid modelers. Any part that is a design space will be reshaped during optimization, while any part that is not a design space will remain as it is. You can have any number of design space in your model. Parts designated as design space are displayed with a reddish brown color as shown below. So a design space can have any shape or topology as long as it is a single solid volume. A part that is used as a design space should not be very detailed. To ensure the most freedom to generate a shape, you should not use the simplest design space possible. The more fine details you have in the design space, the longer it will take to run the optimization. A shape generated by optimization is contained entirely within the volume of the original design space. Since material is only removed, not added, you specify the amount of material to keep either as percentage of design space or by entering a target weight. So below figure you can see the entire volume with the change in the design space. So this is the optimized shape of the bridge. So now I'll show you how to divide a part into design and non-design space. So let's open the STInspire 9.5 GUI. To open it, go to Start, All Programs, Altair HyperWorks, Student Edition, SolidThinking Inspire 9.5. So this will help you to open the GUI of STInspire. Let's open a model, any model. Just I want to show you how to divide a component into design space and non-design space. So as you can see, this is already divided into design and non-design. So if you right click, deselect So this is a normal part with every component in a non-design space. So you just select the part, right click on it and check the box here, design space. So this will become a design space. Similarly, you can make this also a design space. So whatever component you want, you can make it in the design space. In this way, similarly, you can make it a non-design space. Also, once you select a part in the model browser, you can change it into design space from the property editor. Also, here you will find a design space option. As you can see here, if you untick it, it will become a non-design space, but when you check the box, it will become a design space. So the reddish brown color means it's a design space. So during the optimization, the software will remove the material from the design space. So you have to make sure that you put a actual component which you want to optimize in the design space, rest all in the non-design space. Now let's see about the pattern repetition. When an instant part is designated as design space, STInspire will automatically apply pattern repetition to design space so that they generate identical shapes during topology optimization. This is useful when designing a part which exists at multiple locations in an assembly, with each instant experiencing different loads depending on its position in the assembly. So now I'll show you how to create an instant parts. So let's make this non-design and this one with a design. So what you have to do is just select the parts, right click it, copy, again right click, and instead of paste, click paste instances. So paste instances will help us to do the pattern repetition. So if you click on paste instances and move the part, so select these parts and move it aside. Now turn on the rest of the components. So whatever material it will remove from this, the same amount of material it will remove from this, and the same pattern, the pattern will be same. So this will help us to do the pattern repetition. So you have to copy and paste the instances, that's for sure. So you have to paste the instances instead of creating a paste. If you paste it, the optimization will not follow the pattern repetition. So paste instances will help you to follow will help optimization or STInspire to follow the pattern repetition. Now we will see about the loads and displacement. So before running optimization, you need to define at least one load case, a set of load and displacement that acts on your model. Load includes forces, pressures and torque, while displacement includes supports and displacement constraint. These are created by clicking the selectable areas on the load and displacement icon group on the toolbar as shown in the table below. So this icon you will find in STInspire 9.5. So I will show you how to use it. So I'll explain you what are these. So first is to apply force, this arrow. Then to apply the pressure, you can use this. To apply torque, you have this icon. To apply supports, that is constraint, you have this icon. To apply displacement constraints, you have this icon. So all of the loads and displacement in the model are shown in the model browser in a folder called all loads and displacement. The loads and displacement included in each individual load case are displayed in subfolders as well. Any load or displacement can be included in multiple load cases and therefore may appear multiple times in the model browser. Alternatively, a load or displacement might not be included in any load case, in which case it's only appear in all loads and displacement folder. This folder only appears once a load or displacement has been applied. So now I will show you how to create the loads and displacement constraint. So what I will do is I will delete these copied things, just delete, and move it in the center. So F will help to fit to screen and show all. So you can see the forces and constraints are already applied on this. So what I will do is delete all the forces and constraints. So to apply force, you will have this icon to apply force, this single arrow. You can apply the force on edge, like in directions, in angle, just double click to get enter to the editing panel. So you can have it in any angle. So whatever angle you want, you can edit it here in this way. If you want it in 45 degree, just put 45 degree, minus 45 degree. Then you can select the direction. You can have a point load or distributed force, point force or distributed force. You can change the magnitude from here. If you find it in not in Newton, so you can change it from here, let's say LBF, so it will be in LBF. So if you want it Newton, you can have it in Newton. So in this way you can change it from here. You can change the direction, positive, negative, the direction of force. Similarly, you can apply the force on the surface. So change the direction, perpendicular to the surface, positive, negative. In the surface also, point, as this is a curved surface, you can have a center force applying to it in the direction you want. Point force at the surface, perpendicular to the surface, it will automatically be perpendicular. Change the magnitude. So you can apply the force on edge, on the surfaces. Also, you can apply the force on the circular areas, the board location. So you don't need to create the rigids in if you want to apply the force here. So you don't need to create the rigids. You can similarly change the direction. You can have the perpendicular force. You can have the negative, positive. You can change the angle of force in what way you want. If you want some angular force, you can change it like this. It's very simple to change the force here. So you will have the angular force. So these are the ways you can have the edge force, surface force and a center force with the rigids. It automatically creates the rigids. It automatically creates everything here. So you have to just apply the force, give the magnitude, rest STInspire will do. So it creates all loads and displacement folder where it puts forces and a load case. So you can create a load case. I will show you in the later session. Now I will show you how to apply the pressure. You can apply the pressure so apply the pressure on the entire surface in positive, negative direction. The magnitude of the pressure, it will keep it as pressure. You can have the pressure inside the surface like this. Change the magnitude, finalize. So you can add the pressure in much simpler way. So this is the way to apply the pressure. Now you cannot add pressure on the edge. So either you have to select the pressure for on the surface, whether inside or outside. Then the torque, just click on this, select the surface where you want to apply the torque. Here you want to apply the torque. So the direction of torque, positive or negative, clockwise or anti-clockwise. If you want some particular direction of the torque, or in particular angle you want the torque, you can use that. Then the directional axis of the torque, in which axis you want, and the magnitude, Newton per mm, you want to change it, you can change it from here. So in this way you can edit the torque. So these are the ways you can apply the forces. Multiple forces you can apply on the surface. So these are the ways you can apply the torque. Now we will see about the constraints. So this icon is used to create constraints. So you can apply the constraint on edge as like force, point constraint, multiple point constraints. Also the direction, if you want to change the direction of the constraints. Perpendicular to the edge, single and multiple. Then if it's all transparent, that means it's constrained to all the degrees of freedom. If you take any one axis, that means it is free to rotate or it's free to translate in this particular axis. So translation is free. So this in this way you can apply the constraints. I'll again show you. Now you can apply the constraints on the surface. Just select and apply the constraints. So now there is no use of this constraint, it's free for all, so it's not applying. So you have to make it like this. So this is showing the global axis, Z, X, Y. So I am constrained to Y. Here I have constrained to Y and Z. So in this way you can put the constraints whatever axis. If you make it all green, so it's of no use, it will be like invisible. So you have to make sure that any one is active. So in this way you can find it that one axis is active, two axis it's constrained. So in this way you can apply the constraint to edge, to a surface. Also you can apply the constraint on the bold locations. So this is the constraints on the bold location. You can have a point constraint, surface constraints, inside all, and a center constraints with a rotation on. So, and this is constraint to torque, constraint in the direction. So it's free to rotate in that direction. Translate in this direction is fixed. It's free to translate in this direction, but the rotation is fixed. So in this way you can apply the constraint. So you have to just tick it. If I click here, it's fixed. So in this way you can apply the constraints. So I have fixed the rotation. Now the rotation is free and translation is fixed. So it will not translate in this direction. So if you want to apply the constraint, you can apply the constraint in this way. Fix it. This is all free. So if I free it all, so you can see it's free to all. Okay. So once I right click, this component is free to rotate and translate, but if you want to turn off, you can turn off it. So now it is translation and rotation is locked. It is constrained to translate and rotate in this particular direction. Point, you can change it like this. So point, you want in some direction. Surface, you can have this direction, and here you can have the rotation. So in this way you can edit it. So these are the ways to edit the constraints. Just click to add the constraint. You will just need to click here to add the constraints. So in this way the constraints have been added. Now the displacement constraints. So this is a single displacement constraint. So this helps us to define that the part will not displace till this point. So this is the displacement constraint. I can make it an mm. You can reduce the size to 1. The direction, and you can change it to double displacement, so it will not displace in this. So it is allowed to displace further, but now if it's a double displacement, it will not go further. It will only displace in this region, not more than that or less than that. So this is fixed, this is fixed. If you turn off, it's off. If you turn on it again, it's on. So you can turn off this, so it's fixed. You can change the direction, make it perpendicular, and change constraint in one direction, constraints in all direction. So if it's a single, it's constraint to all direction. This ball means a constraint to all direction. It is not allowed to displace in any one of the direction, any direction. But if you want, you can make it to if you make it in the single direction, you can do it like this. So you can apply the displacement constraints like changing it. So single support is capable of reverting translation in XYZ direction. By default, translation in all three directions is locked when the support is first applied, but you can double click the support con to enter editing mode. Once in editing mode, transparency arrow appears, you can toggle translation or fix all. So in this way you can edit the constraints. So the displacement constraint can be applied to a model to limit deflection in desired location and direction. These constraints should only be applied to a non-designed space, and while they can be used as the sole constraints for an optimization, we recommend using them alongside a stress constraint. You can apply displacement constraint to a model using the apply displacement constraint tool in the displacement icon group. They are represented by pyramids that appears orange when selected and blue otherwise. So it's otherwise is blue. So in this way you can apply the displacement constraint. A displacement constraint is applied at a particular point on a model. You can choose to limit displacement in one direction or in all direction, as you can see here. So we have defined in one direction or in all direction the displacement constraint. Now I will show you how to manage the load cases. So it has created one load case, as you can see here. While I am defining the loads and boundary condition, it is defining one load case. So I will show you how to manage the load case or define more load case. So what I will do is just right click here on the load case, create new load case. So you can have case as 1. if you want these things in one load case, you can just drag and drop. So this will come in the 1. So if it's off, this will become the off. Similarly, right click, new, case 2. I want pressure, support, displacement and support 13 in this. So now this has one set of load case, this is second set of load case. So in this way you can edit the load case. It's very fast, quick. Now if I want to delete it like this, I don't want this, it's been problem, so just delete. Here also you can just delete. It's simple to delete. You can delete multiple load cases also. Delete. Just press delete button from your keyboard. So torque, you can just delete. And you can have a copy paste. So copy in this, paste. So you will have a torque constraint here. So a torque constraint can be applied twice. So just copy and here click and paste. So you can have a torque here also. So we have a torque in 3 different load cases. So why I copy pasted it? So for this case, let's suppose I want a torque to be in some other direction. So let's off this. So you can have a copy paste, and if you want, so if you want the torque in some other direction, you can change the direction for that particular load case. So this is for this particular load case. So in this way you can edit it like this. So in load and displacement, there is one point which I want to discuss with you are, why are my results disconnected? When you use displacement constraint, it is important to either apply them near all the major loads or to use both stress constraint and displacement constraint together, as shown in the first 2 images below. If you apply a single displacement constraint 2 mm at the tip of the foot peg, the results are biased to only account for that displacement constraint. The third image shows how the optimized result changes if the stress constraint with factor of safety 1.2 is added to displacement constraint. The resulting shape can resist the stress applied while maintaining a total displacement of 2 mm at the foot peg. So this will be a tip and tricks like for STInspire. Now let's move to shape controls. So shape controls are used to include symmetric shapes, shape with cyclic repetitions, and shape with raw direction for casting and stamping. While optimization always requires the presence of loads and to generate the results, applying shape controls is optional and provides additional design goals that must be satisfied by the optimizer. The 3 basic categories of shape control tools that you can apply to a part are symmetric planes, cyclic repetition, and raw direction. So I will show you now how to use it. Okay, so what I'll do is I'll create a new structure to show you the shape controls. So I'll click new, don't save. Let's have a new structure. It's quite easy to create a new structure from here to here like this. Done. Right click, rotate a model, zoom. So this is the box. Now first we'll start with symmetry. So we have symmetric, cyclic symmetric, cyclic rotation, and cyclic symmetric. So this is the symmetric. So this is planar symmetry along XY plane, YZ plane, ZX plane. So if it's turn off, it will be not a symmetric. You can turn on, be symmetric. If you want to change the axis of symmetry, you can do that from here. If you want perpendicular to the axis, you can have this icon to make it perpendicular to the plane. From here you can change symmetric, cyclic, symmetric, cycle repetition with symmetry. So we'll see cyclic repetition on this model. So 3 sections, you want 2 section cyclic repetition, 10 section cyclic repetition. So how many sections cyclic repetition you want, you can have it like this. Similarly, you can change the angle of cyclic repetition, whatever angle you want. Then again I will click here. You can have the direction in which axis you want the cyclic repetition. You can edit it from the corner, so you just change the number of cyclic repetitions to how many numbers you want, you can change it. So all the patterns will be same along all the components. Then cyclic symmetry. So it will repeat the same pattern from 1, 2, 3, 4, but it will have the symmetry, like whatever here, same as this. So it will have the repetition with the symmetry. So this option will help us cyclic repetition with symmetry, like as it is showing. So cyclic repetition with symmetry, and this will only have the cyclic repetition, means you can it will have the same division across, same amount of material removed as the repetition of the material remover, but the symmetry will be same along this. So like you can have less number of symmetries, whatever, the same options here. Change the direction and change the magnitude also. Want perpendicular to the surface, you can have the perpendicularity to surface. Then I'll just remove it. Then the extrusion parameters, draw directions. So let's see the draw directions. We have 4 draw directions in STInspire. First is single draw direction, split draw direction, stamping and extrusion. So let's start with the single draw direction. In which axis you want the draw direction to be? This axis, this plane. You can move it, the plane you can also move. Holes, no holes. The direction of split, you can rotate the split axis if you want. You want to translate it, just translate it. So in this way you can translate or make it to perpendicular to the axis. The center of the component. Then you can change it to split draw. So this option will help us to create a split draw. With, if it's on, that means it will not create any holes. If it's turned off, it may create a hole. So no holes and holes during the splitting process. Direction, then same axis, center to the geometry, and they align to global. So this will help you to align to the part, align to the global. So if you change it, anything you change like this, and you don't want like, so you can align it to global. It will get aligned to global automatically. So it's very easy to change the settings in STInspire. Now we will see stamping. Stamping with holes, no holes, the direction of stamping, the angles, align to part, align to global, the same options, and extrusion process. Extrusion process will never have that hole or no hole option, but will have the direction, in which direction you want the extrusion process. Align to part. If you want to change the global axis, you can change it from here. If you want to change it on along any one axis, you can change it to along the axis. So from here, if you want to start, from here if you want to start, you can change it like this. If you want it in some plane, you can move it to the plane also, or else just double click align to part. So it's aligned to part. So in this way you can edit the shape controls by extrusion. Just right click to go to the main menu. So some draw directions and symmetric results. So these are the options available to which you can use in STInspire to get a good results. This really helps to get a good results. I'll show you in the tutorials that how the shape controls help to get a better results after the optimization. Now let's move to the last topic of today's session, which is running optimization. Options available which we can use to perform a run in a STInspire for the optimization. So optimization generates a shape for each design space in a model in response to the load on that model. It carves material away from design space, creating the lightest shape possible to withstand the force that you apply to the model. You perform optimization by defining at least one design space and one or more load case that contains loads and support. If desired, you may also apply displacement constraint and shape control. Then you run an optimization and await the results, which can take few minutes to a few hours depending on the complexity of the model. Once the results are complete, you can interactively explore variation of the result shape. In general, it is best not to apply loads and displacement directly to design space, as this often leads to incorrect results. Instead, you should split the part into design and non-design space and apply loads and displacement to the non-design space. When you run an optimization, you specify the name of the run and optimization objective in the run optimization window. Depending on your objective, you may also want to define displacement constraints, mass targets, stress constraint, frequency constraint, thickness constraints, and whether or not gravity should be applied. Inspire perform check to ensure that the model is properly prepared and load cases are checked to verify the appropriate support to the load exist. If any problem is found, you are given help on how to correct them. Let's see what are the options available in. So now let's see what are the options available in run optimization. Let's open the same model. So this icon is used to enter to run optimization panel. Just click, it will have a tab here. You can move the tab anywhere you want. And this is the run history. Whatever run you do, you can check it from here. Once it's run, you can see the solution here. As you can see, this is my model. Don't save. Click new, don't save. So from here I can just open the model, the results model, you can see. So this is the result model. If I click here on this, so this is my optimized shape. I can change this topological shapes variation. So in this way you can do it. New. So this is the run history. The first icon in here is run history. Then run optimization status. This will help us to see the run optimization status. So whenever you click run, it will start automatically. So this is history. If you want, you can delete it all or check the run optimization status. Now I'll show you the run optimization tab, what are there. So we'll start with the name. First is the run name. So I will first start with the run name. You can put any one run name, whatever you want. So run name, specify when you run an optimization, the name of the run defaults to the name of the part used as the part design space. However, you can assign your own name to the run optimization window. When a run is made, the name is appended with several parameters to identify it, including the optimization objective, mass target or safety factor, stress constraint, frequency constraint, and whether a displacement constraint has been applied, as well as counter that is incremented each time you run an optimization on a particular part. So these are the details. It comes along with the run, name of the run. So I will put it as run 1. You can change any one. Then objective of the optimization. So there are different objectives of the optimization. So when running an optimization, you must decide whether your objective is to maximize the stiffness or minimize mass. So there are two objectives: maximize stiffness, minimize mass. If you maximize the stiffness of the design space, the resulting shape will restrict deflection but may be heavier as a consequence. If you minimize mass, the resulting shape will be lighter but may deflect more. Give a particular design space and a set of load, displacement, shape controls applied to your model. You will see different results depending on which objective you select in the run optimization. So depending on your objective, you will get a different results. So if you select maximize stiffness, so maximizing the stiffness of a design space will result in shape that is the stiffest possible for a given mass. If you select maximize stiffness as your optimization object, you will need to specify one or more of the following. First is mass target, second is frequency constraint, and the displacement constraint. So these you have to specify. If you select maximize stiffness, then if you select minimize mass, so minimizing the mass of a design space will result in shape that is lightest weight possible, which can still support the applied load. If you select minimize mass, your optimization objective, you will need to specify one of the following: stress constraint, frequency constraint, and displacement constraint. So the minimize mass optimization objective is normally used with stress constraints. One, optimization is complete. The best results with minimize mass is generated found by dragging the topology slider for far right to the shape explorer window. The optimization results is the point at which all the loads and support locations are connected. So this will help us to define these constraints. Now I'll show you the other options, that is the mass target. So when your optimization objective is to maximize stiffness, mass targets are used to specify the amount of material to keep. This target can be defined either as percentage, if you click here, so either as the percentage of the total volume of the design space or as total mass of the entire model. If you have more than one design space, you can set target of each design space individually. You can also set the mass target to none. So if there is no mass target, you can select it none. So percentage of total displacement, if you select, this means one portion for specifying a mass target is as percentage of total volume of design space. For example, if you specify 30% mass target, then 70% of the material is carved away from the design space, leaving 30% of original material. You can specify more than one mass target percentage at a time, with each target producing a separate run. Note that optimization may not always produce an answer for every percentage you specify. As the lower the percentage, the more challenging it is to produce the answer. Typically, percentage range from 20 to 50%. Then if you select total mass, so a second option for specifying a mass target is to enter the mass of the entire model. This is the total mass after optimization. So including both design and non-design space, you can specify more than one mass target at a time by entering values separated by comma. with each target producing a separate run. Keep in mind that lower the mass target, the more challenging is for the solver to produce the answer. Then if you select specify per design space, so if you have more than one design space in your model, you can specify the mass target at each design space individually. Choosing this option opens a table listing of all the design space where you can enter a target mass of each. In the table you can specify a mass target directly, or you may enter a target as percentage for design space mass. So you can put a percentage like 40%. So target mass is like current mass to target mass, you can have like 10%. So you can change it, or you can put it like from target mass to here, the actual mass to target mass. If you want it in kg, so this is the kg, it's 0.74 kg, so 10% of 0.74 is 0.74, 50% is this. So it will keep this, rest it will remove. So these are the options in mass targets available in STInspire. Then the stress constraints. So if you select minimize mass, you will have the stress constraint. Global stress constraint can be applied to limit the maximum stress in the model, and is used when your optimization objective is to minimize mass. Inspire analyze the material used in the model to determine which has the lowest yield stress, then divide it by its minimum safety factor. The higher the safety factor, the more material will be added to the optimized shape. To limit the overall stress in the model, stress constraints are automatically enabled when minimizing mass. The motorcycle bracket picture, as you can see, will help you to understand that. So if you can put none, you can have the minimum safety factor like 1.2. I want minimum safety factor or factor of safety to be 1.2, not less than that. So you can put it like that. So this is the option available for stress constraint. Now the rest of the other options are same for both, they doesn't change. So whatever option you select, the frequency constraint, thickness constraint is same. So I will now explain you what is frequency constraint. In some cases you may want to change the natural frequency of an object so as to avoid resonance with other parts in your design. If you want to control the frequency at which an optimized part vibrate, you can set frequency constraint before running an optimization using the run optimize window. So you can have the frequency like maximum frequencies, use supported load case, so for which load case you want, or minimum frequency, this will be the minimum applied to the lowest 10 modes. This will be the minimum, it should not go beyond this. So when maximizing stiffness, you may choose to either maximize frequency or set a specific minimum frequency. If you choose maximize frequency, Inspire will automatically maximize both the stiffness and frequency of the model, and the lowest natural frequency will be displayed in the Shape Explorer window. If the resulting frequency is not high enough to meet your constraint, you may need to assign a stiffer material or modify your mass target for the optimized shape. When minimizing mass, you may enter a specific minimum frequency and specify how many of the lowest mode must exceed that frequency. If Inspire is unable to achieve the specified frequency of the lowest mode, this will be flagged in the Shape Explorer window, or in the certain cases the optimization run may fail. If this happens, try assigning a stiffer material. So changing this will help you to get a stiffer material with a frequency range. You can also control the frequencies of your model. Then the thickness constraints. So when running an optimization, you can control wall thickness and diameters of beam-like members and a shape by specifying a minimum or maximum thickness in the run optimization window. Wall thickness and beam members. So minimum and maximum. So Inspire provides wall thickness and beam member thickness are controlled by the same parameters. Inspire provides default values for both thickness constraint. The maximum thickness constraint is only enabled if minimum thickness constraint is enabled first. So first you have to enable minimum thickness, then only the maximum thickness is enabled. The default minimum thickness is 3 times the average element size. The default maximum thickness is 2 times the value entered for minimum thickness. So whatever you specify here, if it's the minimum thickness is not active, you cannot have the maximum thickness directly. So the minimum thickness is 3 times the average element size, and the maximum thickness should be 2 times the value entered in the minimum thickness. So if I turn on maximum, and if I want it 0.0001, so it will give a warning. You can see the maximum thickness should be set to at least 2 times the minimum thickness. So change it to the 2 times, it will automatically change. So now let's go to the gravity. So now gravity. If the weight of the structure is a significant portion of load it is bearing, then you should include gravity when running an optimization. Larger objects like building and bridge must support their own weight and should have a gravity applied to them, while small stiff structures that don't flex under their own weight should not have a gravity applied. When applying gravity, you must always apply some force, pressure and torque to your model as well. If there is no force or other forces are very small relative to the weight of the structure, optimize will result an empty structure. Gravity pull towards negative z axis by default, but you can change the direction of the gravity. I will show you how to change the gravity. So if you want to change the gravity, like for this model, this is the direction of my model. Let's say my model is in this axis. In this way I am going to put it like this. So my gravity will work in positive x-axis. So you can change it from here, positive x. So it will now the gravity act will downward. So you have to see the gravity of your model, and accordingly you have to apply the gravity. And you can select here the load cases. From here you can select the load cases for which you want to run. So if you select all the load cases on your model browser, so the optimized result will have the shape supports for all the load cases. But if you have a specific run, so then the optimized shape will have the optimized shape will only specify the results of the one particular load case. So it depends on individual and the components how you want to use the load cases. So you want to turn off, turn on, reverse. So you have multiple load cases, just reverse. You can export the file to FEM. This will help you to solve in the HyperMesh. So this will help you to prepare and export to OptiStruct. So this way you can create an FEM file of this model and export it to FEM, and then open it in HyperMesh. You can import it in HyperMesh after its export. So in this way I have covered the optimization options available in STInspire. They are as shape controls, loads, displacement and optimization. Material also comes in this, but material I have already discussed. So with this I have covered all the tools available on the GUI of STInspire, how to use them, what are the different options available in that. So I have covered all these things. So lastly I will show you I have exported that file into FEM. So let's open HyperMesh and import that file. So I will select that file, import to optimization, close, hide the load cases, hiding the system. So this is the model with a design space with all the different components and with a proper meshing done already. So with the rigids and all. So it already have everything. So the material you assign, it will have that material also. So whatever thing you have, it will automatically update. So in optimization, say topology, go to update and select it. So it will have the parameters. It doesn't have any draw direction, so it will not have. Then in the responses, if you see, it has the responses, volume fraction, mass fraction, frequencies. Then in constraints, you can see that these are the constraints, and the objective will be, you can see. So everything it has, it creates by default materials, and then the properties, design variable. So STInspire creates the complete set of topology optimization, or you can do in hypermesh also, but it's very easy to use it. So that's why I just show you how you can use the STInspire to get a optimized shape quite fastly. So you can see here it's quite easy to handle here and change the design components. So if I want to change the thickness here, I can simply change it to thickness. Done, man. The thickness has changed, you can see. If I want this whole till this, yeah. So yeah, this is through. So in this way you can edit the model quite easily, and in this the meshing is automatically done. So if you select here the design space, if I scroll up and turn off this, I want an mm. Let's say I want an mm. So my minimum element size, let's say 0.1, and the maximum will be 1. So again I can go to file, run optimization, export the file again. Let's see what difference it has. Okay, so this is the old, again the new. Go to import, select the file. This is one. Import. So it will take a little time to open it, because I think the element size is drastically increased. So I have given a very less element size, that's why. So hide the load collectors, hide the systems, press F from the keyboard, mesh. You can see it has done the meshing with the dense element size only for the design space, because I have given the parameters for the design space only. So if I turn on this and this, so they have the overlapping. So these are the rigid faces. If I press F, this different rigid spaces. You can see, and on this and this. So in this way, just change the meshing or change the boundary condition will help you to get the results here. So in this way, I have ended with this 6th day of the training series. Thank you very much for attending this session. I hope you like that training session. If you like it, please let me know. Share your comments with me at edu-support@india.theatre.com. Also, if you find any queries, let me know. Will help me out to solve your queries. Thank you very much for attending the session. Have a great day ahead.